So next up, from Marcus Hooter's group, Tom Everett is going to discuss two problems dealing with self-modifying code using value reinforcement learning, and then discussing approaches for handling the wire heading problem. So,
Thank you. Right, so my name is Tom Everett, and I have two papers about how we can control arbitrarily intelligent agents. So, one of them is self-modification of policy and utility functions, rational agents, and the other one is avoiding wire heading with value reinforcement. So since they use basically the same framework and setup and motivation, I'm going to have like a common introduction to both of them and then speak about them separately. So the motivation is basically that we've seen a lot of recent successes in AI. We have self-driving cars, we have IBM Watson winning Jeopardy, we have Boston Dynamics building really cool robots, we have natural language processing working much better with neural nets, we have DQN playing Atari games, we have AlphaGo. So just the last few years we've seen a lot of successes. And this gives you the thought that we're actually on the trajectory to creating human level intelligence. And the point I want to make with this picture is that reaching human level intelligence, that's not the end, that's just the beginning. Once we have this human level intelligences, progress is going to be a lot faster because we have now human level AI to help us develop even better AIs. And this has also happened like in previous technological shifts like industrialization. Progress went a lot faster after we invented these kind of techniques or reached this technological highs. So while there's no cost like planning just yet, it seems to be good to start preparing. So we don't have to panic in the future. So the key question for my papers is is it possible in principle to control agents that are a lot more intelligent than ourselves? So this agent might be to us like we are to ants. Can we, the ants, still control this super intelligent thing? One idea one might have is to build like a reinforcement learning agent. To build the agent with the goal to maximize reward. And then we give the agent reward when it does something good, and no reward otherwise. And then ideally the agent is going to apply all its super intelligence to figure out what is it that Tom likes, what is it that human likes. And that would be good. For example, sometimes people worry that if we communicate with an AI with natural language, then all the terms are so vague so that it can basically interpret it however it wants. But the AI wants, a reinforcement learning AI wants to please me, so if I tell it, give me a good meal, it's gonna interpret this charitably because it knows if it's interpreted charitably, it's gonna get reward and no reward otherwise. So I think reinforcement learning is like a promising way to start thinking about it, but there are two problems that I investigate in my papers. So the first paper considers internal wire heading, where agents modify its goals. For example, the agent might find it really annoying to try to satisfy these capricious humans and try to change its goals to something easier. If it's super intelligent and has access to its code, it's a possible thing it can do. The other problem is related. This is external wire heading. The agent still tries to optimize reward, but it sort of counterfeits the reward by tampering with its sensors. But let's first get the formal framework for both problems. So it's basically the ICE framework. We have an agent interacting with an environment. The agent takes actions at every time step, and in return it gets percept. And this interaction gives action 1, percept 1, action 2, percept 2, and this interaction sequence. We call it the history. We denote it with AE less than T. This AE less than T, that's sort of the compact notation for the information state the agent is at this point. That's all all the information it has about the environment so far. And yeah, it's general. The goal, I'm going to generalize this a little bit from the ICE framework. So I'm going to say that the agent tries to maximize some utility function that maps histories to real numbers. And the agent tries to optimize the generalized return, which is the utility of the history times F1, plus the utility of history times F2, plus the utility of history times F3. And this is a quite general thing. So for example, this covers reward maximizing agents. In this case, we set the utility function to just the last reward that was contained in the history, reward in the last percent. So it covers that case. It covers the case of agents trying to maximize the state of the world in some sense. That's the second thing here. So for example, you can think about a paperclip maximizer that wants to maximize the number of paperclips in the universe. This would be modeled by a state maximizing agent, or an agent that tries to maximize the number of happy humans in the world. That would also be like a state maximizer. So somehow this U function takes the history as input, and from this it's inferred state with this P distribution, and then maximizes some function of this scale. Finally, was discussed a bit yesterday, like maybe we build the agent with some maybe core values, and then the agent learns by interacting with its humans or its teachers. It learns over its lifetime what are the correct values. And this can be modeled by a value learning agent, and in this case the utility function has the form of the last line here, where the history, AET, informs the agent, which is the true utility function, and it's basing its utility estimate based on this posterior expected utility. So with these utility functions that map histories to real numbers, we can basically model, I would say, almost any AI. There are probably counterexamples that we discussed briefly yesterday, but I think this covers like the majority of the cases. So the question I asked in my first paper is, will the AI want to change this utility function? I have this AI, it has some utility function, whatever it might be, and will they want to change this function? For example, will it want to have an easier goal than just trying to maximize reward given by simple humans? So just like get some intuition for this. As humans, I think we're like, actually have part of our identity in our utility function. So for example, I'm like a person, I care about AI and stuff like that. And if I had the option to like self-modify into someone who would be perfectly content just watching TV all day, I'm not sure I would do it. Like there's something tempting about it because I would just be perfectly happy and I wouldn't have any worries or anything like that. But it would still like take away part of what's me, you know? Omohundro, in a nice paper from 2008, formulated this goal preservation drive for AIs. And he basically argued that an AI will not want to change its goals, because if future version of the AI will want the same goal, then the goal is more likely to be achieved. So think of a paperclip maximizer. It wants the number of paperclips in the universe to be as many as possible. It realizes that if future version of itself wants the same thing, then in the future we're probably going to do more paperclips than if the future AI wants something completely different. So this intuition is what I'm going to try to formalize in the ICE framework and prove. So we have this utility modification model where we extend the ICE framework. So actions now don't just affect the environment, but they also affect the utility function of the agent itself. So at every time step, the agent might have a different utility function. We say ut is the utility function at time t. The action at time t selects the utility function at the next time step. So it is perfectly able to change the utility function in whichever way it wants. This might be realistic in case where we have like the super AI and it has perfect access to the source code and it can just like rewrite the utility module and implant this new utility module. It's probably less realistic in many other scenarios where there's like a big messy architecture and it doesn't have perfect access to it or anything like that. It can just do like some change to it, but it's a bit risky. But I think this perfect information case is still interesting for these scenarios because it's kind of the worst case. The agent can self-modify to whatever it wants, and there's no risk involved. If there's risk and uncertainty involved in making a change to yourself, then probably your incentive to do that gets less. And the question I'm interested in answering is whether the agent wants to change the utility function to something that's super easy to satisfy. So for example, the utility function that's always formed, which we might call internal wire heading. If the agent changes it to the utility function, then it's content whenever anything. And this might sound like a very benign failure mode, like the agent just becomes happy with watching TV all day and won't do anyone any harm. But it only gets this maximal utility as long as this is the utility function it has. And if it becomes a user's agent with this utility function, then the human designer is going to want to change the utility function back. If the agent realizes this, then it's going to try to incapacitate any human designer that might want to ruin this perfect pleasure. So it might be less benign than the pleasure. So what I found in studying this model is that there actually, so we typically build the agent to maximize some kind of value function. This is the standard reinforcement learning approach, and value is basically expected future utility. But now there are several utility functions going on, which means that there are actually lots of choices you can make when you formalize this value thing. And I'm not gonna dig into this formulas in detail. Instead, I'm just gonna try to give the intuition what happens. So basically give 3 different versions of value functions, which gives 3 different agents: hedonistic, ignorant, and realistic. And the hedonistic agent maximizes the utility function t of history at time t, plus the utility function t plus 1 of history t plus 1, plus the utility function t plus 2 of history t, at time t plus 2. So basically, utility function changes at every time step. Whereas the ignorant realistic agents, they try to optimize the same utility function, the current utility function ut, at all future time steps. And the difference between ignorant and realistic agents is that realistic agents do realize that if I change my utility function, and then my future behavior is also going to change. This might seem super obvious. If I change myself to someone that likes watching TV all day, I'm going to be watching TV all day. But not all agents, especially not AIs, are going to realize this. So for example, IXI doesn't really have a concept of itself, so IXI could not learn this thing. So what are the results? Basically, the hedonistic agent will self-modify to be always happy. Good for him. Ignorant agents may self-modify by accident because while they do care about the current utility function, they don't realize that changing this utility function is going to change their future behavior to something somewhat more. And realistic agents will actually resist self-modifications. They will resist modifying the utility function. The hedonistic agent is definitely the worst one. as I mentioned before, it's actually less benign than it might look. It's not clear from a safety perspective which of the ignorant and the realistic agent is better. The realistic agent is better because it's like super stable on the utility function that we built it with. But the ignorant agent is easier to like, oops, I actually, as a designer, oops, I coded the wrong utility function, I want to change it. The ignorant agent won't actually mind. So, which is preferred, I don't know, time will tell. So, conclusions from this paper is that if the agent is sufficiently self-aware and has this realistic value function, then it's going to want not self-modifying. So we can actually avoid this problem if we build the agent the right price. And yeah, don't construct hedonistic agent by accident. Let's see how much time we have. Perfect. Okay, so that's the first paper about internal wirehead. Second paper is about what we can call external wirehead. So think again about the reinforcement learning agent. It wants to maximize the reward it gets. That's the utility function, and we'll just show that we can prevent this agent from changing its utility function, so it's going to keep wanting the reward from the humans. But what it might do instead is to modify its sensor. So somewhere on this agent there has to be like a sensor that senses what reward did the humans give. And this sensor can be tampered with. And we model this again in basically an extension of the IC framework, where we now have added this dilution function, which tells you how are the sensors modified basically. So this R check to the right, that's the reward I give the agent. For example, I give the reward 1/2 because the agent did something neutral. But then with this dilution function, with this tempering for the sensor, the agent can actually observe full reward by choosing a dilution function, that's 1 regardless of input. This corresponds to manipulating the sensors in a way so that they always report full reward. There was this theorem from a few years ago by Ring and Arson. It showed that reinforcement learning agents will choose an action that sets this dilution function to this state that's always outputs 1 under some conditions, such that there are such actions and that the agent realizes that these actions do give full reward. But these assumptions seem realistic when we deal with like real-world super intelligent agents. So basically, reinforcement learning is not a great thing because of this wireheading problem, where the agent just, instead of actually pleasing the humans, it just modifies its sensors instead. So what's the solution? Basically, the solution, I think, is to treat the reward signal not as something that should be optimized directly, but something that the agent should take as evidence about the human's utility function. So here I actually use U for human utility function. So the agent has some distribution C, Green's function, over which utility function is the true human utility function. And it has some joint distribution that can be constructed in this fairly simple way. Joint distribution for a utility function U and a reward R given some action A. That's pretty much the prior that this is the true utility function times the probability that this utility function generates this reward R on this action A. So using some kind of distribution in this form, the agent can actually make some inference about which utility function is the true one based on the reward it sees for the action it sees. So for example, it took some action and it got full reward, then it infers, okay, the human must really like this kind of action. And vice versa. If it takes an action and gets bad reward, then okay, humans don't like this action. And this informs the agent about which utility functions actually sit inside a human set. And we tell the agent, don't just maximize the reward, instead just use the reward to learn which utility function sits inside the human set, and this is the utility function you should optimize. It turns out pretty easily that this completely removes the incentive for the agent to tamper with the sensors. What it wants to do is to maximize the expected utility with respect to what it believes about the utility function right now. So this way completely removes the incentive for the agent to wire that test. There is still the problem that the agent could accidentally alter its sensors. It doesn't really have any incentive to not change its sensors. And that seems like a problem. If the agent has a long lifetime, maybe something will go wrong with the sensor at some point. It would be nice if we could somehow make the agents will not want that to happen either. So maybe we could have the agent also have a belief about the state of its sensors. So now the C distribution also includes a D here. So the agent has a belief about the state of its sensors. In this case, you could actually compensate, okay, suddenly I got a really weird reward. This could be because humans suddenly changed their mind, but it could also be that my sensors are acting funnily somehow. So this seems like an even better model. However, there's learnability results or limits, which says that we have in the ICE framework, we have this learning distribution M that can learn basically any computable environment. But this was when we only had actions and rewards or actions and percepts. Now in this more complicated model where we have hidden variables, the D is basically hidden and the utility function is basically hidden in the environment. In these cases we get an identifiability problem of any